This is the 4.8 to 4.10 review, number 10, the free response, and calculators are allowed. If we look at part A, we are given information about the velocity of the function along with the graph of that function on a closed interval from 0 to 7, and we were given a piece of information about the position at a particular time. So in part A, the first thing they're asking us to do is to find the acceleration of the particle at time t equals 6. Well, we know that acceleration is the derivative of the velocity. So if I take the derivative of this, I will move through the 3, hit the cosine, inside left alone, derivative of the inside. When I go to this, I'm going to rewrite it as a t plus 1 to the negative 1 power. So if I do the derivative of that, it would be a negative 1 times a t plus 1 to the negative 2 times the derivative of the inside, which is 1. If I simplify this, not that I have to, but if I do, I'd get a negative 3 sine of t minus a 1 over a t plus 1 squared. Our goal now is to compute this at 6. So we will plug a 6 in. And you can leave it like that, or you could give me the decimal approximation, which would be 0.817. So for this you get 2 points, 1 point for the derivative and 1 point for plugging in the 6. And either one of these answers would be correct. If we move to part B, we'll want to find the position of the particle. So let's remember that the position will be the antiderivative of the velocity function. So the derivative is that velocity, which means if we want to get the position, we need to go backwards. So we need to ask ourselves, what did we take the derivative of that generated this? Well, we'll move through the constant, ask what did I take the derivative of that gave me cosine, and the answer to that question is sine. And here we have a power of t, which is a 1 on the denominator. So this looks like the derivative of a log natural. So the antiderivative would be the log natural of the absolute value of t plus 1. Now to make this a general antiderivative so that we get the entire family of curves, we would need to add the plus c. Now, one thing to keep in mind here is that up at the beginning I told you that t was always positive. So no matter what value of t I choose, this inside of the absolute value will end up being positive. So we can write that x of t will be 3 sine of t plus the log natural of just a t plus 1 without the absolute value. The next thing we need to do is we need to use the point that was given to us in order to determine what that c is. We were told at the top that x of 0 is 10. So that means if I plug 0 into this, I should get a 10 out. So let's do that, and we'll get a 10 as the position when I plug a 0 in. And we need to solve for c. Well, this is 0, log natural of 1 is 0, so we end up with a c that equals 10. Because c now equals 10, we know that x of t will be 3 sine of t plus the log natural of a t plus 1 plus a 10. This, I think, was worth 3 points. 1 point for the general antiderivative, 1 point for adding a plus c, and 1 point for figuring out what c is to give us the final result. Okay, last part C says on the closed interval we want to find the time at which the particle is furthest to the left. So I see this suffix of est. That should be reminding me that I'm dealing with some sort of a maximizing or minimizing. And if we think about the particle, it's moving on the x-axis. So we're going left and right and left and right. And farthest to the left will actually be the smallest x-coordinate, or the smallest position value. So we are going to be minimizing the position function. So we can write down that position has its min either at an end point or a critical point. since we're on a closed interval. So the critical points are when the position's derivative, or when the velocity, equals 0. And since we want a min, we want it to change from negative to positive. So if we go up and look at the picture way up here, we can see that this is going to represent a maximum on the position curve, and this one is going to represent a minimum on the position curve. So really, this is the one that we want to look for. So we're going to pull our calculators out here and go to our y editor, and it looks like we've got y2 is my derivative already. I'm going to let y1 be that position function that I figured out in part B. So I'll put that in, which will be a 3 sine of x plus a log natural of x plus 1 plus 10. So now I'm interested in finding the point on the velocity curve that crosses the x-axis, so we're going to turn off y1 and we'll graph y2 in the window that we were given up here. So that looks like 0 to 7 and negative 3 to 4. So I'm going to change that window. So my x min is 0, x max is 7, y min is negative 3, and y max is 4. Or excuse me, yeah. Then we'll graph this. And remember, we're going to be looking for this x-intercept right here. So we can do F5, look for the 0. We're already on the left. The right looks like 6 would probably be to the right of it. And we've now found the location, which is 4.653. So what I'm going to do now is down in part C, I'm going to test x of 0, x of that point we just found, and x of 7. And remember that we have our position function stored in y1. We also know from the given information that when we plug 0 in, we got 10 out. So now we're just going to have to plug this into y1, and we're going to have to plug 7 into y1, and then compare to see which one is the largest or smallest. So to do that, we'll go to the home screen. Let's recall that that x coordinate that we just found, the 0, has been stored in the calculator as xc. So I can do y1 of x alpha c, and I'll get 8.737 as an output for that critical point. And if I plug 7 into y1, I'll do diamond enter, I get a 14.050. So we can see in this list that this indeed is the min. So x has a min of 8.737 when t equals 8.737. Oops, excuse me. Might help if I put the time down. 4.653. And we're done.